Hey everyone, can you hear me? Is this working? Awesome. Hi, my name is Tamar. I work for GoDaddy Israel, and I'm going to tell you a little bit about what we did in our Ruby app when our data needs grew too big for what the default Ruby stack could handle, for us at least. So the agenda, a trick I learned yesterday, this is not a technical talk, right? So I'm going to start with just a short description of what is GEM and how it's built. And then I'll describe the problem, like why am I here talking to you, why it stopped working for us. And then I'll kind of walk you through the different things I looked at, the different solutions I explored to solve this problem, and of course, presenting the end result at the end. So what is GEM? Well, GEM not in the Ruby context, but in the GoDaddy context, it stands for GoDaddy Email Marketing. It used to be a company named Mad Mimi that was bought by GoDaddy about 3.5 years ago. GoDaddy, for those of you who might not know, it's a name for a collection of applications that provide web services for small to medium businesses. And one of them is email marketing. Email marketing essentially is just an easy way to send nicely designed, fully featured HTML emails to your clients, so to your all of your contacts. So say, for example, you have a book recommendation thing, and you want to send your monthly recommendations. You can add all of your contacts in GEM and then send them your recommendations. Or, for example, if you have this cool retro clothing shop in Boston, and people want to register because every time you send different things, you get different things from around the world, so you want to send updates about the new cool things that arrive to your shop. So maybe in addition to just the emails of the contacts, you also want to store additional things. Maybe you want to store lists of people who are more interested in accessories. Maybe you want to store people who are more interested in boots or in jackets or in dresses. And maybe even people want to give you their height so you can find articles that are specific to them. Maybe they want to give you their birthday so you can send them special promotions on their birthday. So in addition to just storing emails, we're also storing a whole lot of other information. Some default fields like address and birthday, but also custom fields that you can define for your business needs. Our stack is a traditional Ruby stack. We have MySQL in the back. We use React in the front. We use Passenger. We use Sidekick. And it's been working well. So what is the problem? Well, the problem is that kind of like this cute little mouse, we chewed a little bit more than we could swallow. So as Mad Mimi grew, and later turned into GEM, we had more and more users, and our users grew themselves, right? So we ended up with a contacts table that's over 1 billion record, and it's not just, million rows of data. It's very rich data. It has a lot of relational information attached, and it has a lot of indexes because we want to allow people to search on this. So that's like one part of the problem, but then another part of the problem is that all of these additional fields that I described were stored just as a YAML blob on a SQL column. So if we want to allow these rich searches, of course, you can brute force them, but it's not going to be very performant. And my pro tip of the day is not to do a record count when you have such a big table. So about 1.5 years ago, my boss came up to me and said, hey, we know this problem is coming, right? We know that our contacts table is becoming bigger and bigger. We have over 1 billion. We need to find a solution. And this phrase keeps being thrown around, right? Well, over 1 billion. We have over 1 billion contacts. And I was like, okay, I want to know, like, beyond the buzzword, how many contacts do we actually have? So what do? I go onto the production console, duh, and I put contact.count. And then I wait for a few seconds as it's freezing, and then I start freaking out that I'm going to crash, the production database or server or whatever. So I Control-C, and I did not crash the server, but I also never got an answer to the question, how many exactly? Somewhere between 1 to 2 billion. So, okay, this is the premise of the problem, but when we started exploring it a little more, we understood we actually have the problem is bigger than just the GoDaddy email marketing, because as I mentioned, GoDaddy is a collection of web applications. And other services also have this concept of the secondary customer information. So not the direct GoDaddy customers, but the customers of our customers. So if you have an online store, the people who buy on your online store are a form of a contact. They are that second circle. If you have a website from the GoDaddy website builder, people who visit your website can be considered, again, as the secondary entity. So we realize that this problem is not only for GEM, is not only in the email marketing world that we're dealing with, but it's actually a broader problem, which means that the solution that we want to find, it needs to be scalable not just to the 1 or 2 or 3 billion for GEM. We want it to be, we want to be able to throw 10 billions on it and still, like, I don't want anyone contacting me on my weekend. Like, weekends are sacred. So we want a system that is highly scalable and also highly searchable. For what I said before, we want all of these fields to be accessible to the user so they can make their queries on their contacts. So from what I described before about how we wanted to be able to really scale, we figured that SQL is not the right solution for us. While you can shard your own SQL, it's a little hard. There are some new solutions to shard SQL for you. But you're still going to be bound by the limits of the machine that the SQL is ran on. So for scalability, we decided to go with Cassandra. Cassandra is of the NoSQL family. I personally think Cassandra is a very interesting data store because while it is a NoSQL and has a lot of the NoSQL limitations that were mentioned before, its interface is very SQL-like. It has a query language, the Cassandra query language, the CQL, that is very much like SQL. And I'll show you later why that is actually a bit of a problem when you come to develop against it. But Cassandra is also highly optimized for writes. So it can take a heavy load of data, but it's not very easy to run queries around that data. Because of the distributed nature, highly distributed nature of Cassandra, basically storing partitions, bits of data can be on different locations, it makes it very hard to search it in a performant way. So we decided to add on top of it Elasticsearch. Because it's Elasticsearch, it's for searching. The reason we're not using Elasticsearch as our only data store is because from our experience, it has not been stable enough. We've seen downtimes, problems with garbage collections. There are resiliency issues, meaning you're writing to the server and it says it got the data and then it's just not there. If the Elasticsearch version 5 is said to have a lot of improvements in that regard. If it does prove to be stable enough, we might decide to drop the Cassandra and just use Elasticsearch. But from our experience so far with the Elasticsearch 2.2 at least, it hasn't been, well, I should say, with the, in other projects, it has not been stable enough for us to use as our only store of data. We needed Cassandra as the source of truth. So if the data gets corrupt or if it's completely down, we can re-index and we can do basic queries. Okay, so we've decided we have Cassandra, Elasticsearch, we have Ruby. What more do we actually need? Why am I even talking here today? Well, now comes the real question of how are you going to mesh all of these things together? Because unlike the active record, well-traded root, there aren't like built-in, out-of-the-box solutions to how to do it. And at this point, I have a confession. Please don't kick me out of the conference. The prototype was written in Node. There, I've said it, it's off my chest. You all know now. So, moving on. The first solution that I looked at is a project called Alessandra. Alessandra, exactly like it sounds, it's an open source project that puts Elasticsearch on top of Cassandra, and it gives you a one-stop to do your writes and your reads, and it handles everything for you. The problem with Alessandra was that a year and a half ago when I looked at it, it was an open source project by 2 guys in France. It was still stuck on Elasticsearch 2.2 and Cassandra 2 point something. It wasn't very maintained. It obviously didn't have support. And we figured it was too much of a gamble for us to go with that solution. I did look at it again for this talk, and it has grown really well. So it has over 800 contributors, thousands of commits, and most importantly, commercial support. But at the time, it just wasn't the right solution for us because it wasn't mature enough. So we decided not to go with Alessandra. The next thing that I looked at was DataStax Enterprise. DataStax is the company that does Cassandra, and they have an enterprise product that gives you search, it gives you graphs, it gives you a lot of other things. So I thought, okay, that sounds awesome. They have a Node driver, so I plugged it in my Node prototype. And it works, it does everything that we need. Again, it's a one-stop shop, looks perfect. So I go to my boss, I say, hey, I think this works perfect. And he's, okay, I'll go talk to the salespeople of DataStax Enterprise. And he comes back and he's like, okay, no, that's just not gonna happen. It's just way too expensive for our budget for this project. So it's a good solution, but it's also a very expensive one. And we just decided it wasn't right for us because it was too expensive for this specific project at least. Okay, so until now, I looked at two solutions, and both of them were one stop, right? So I can write my data, don't have to worry about anything, and then I can read my data. But then if I can't have this one-stop solution, what does it mean? It means that when a request comes in, I need to write it both to Cassandra and to Elasticsearch. So if at the end of this request, the data in Elasticsearch and in Cassandra is different, how do we know which one is correct? We're facing a data integrity, possible issues with data integrity. How do we know which data is right and which needs to be corrected? So we talked with other teams, and they suggested we use Kafka. So we use Kafka. So Kafka is a messaging system. It's a messaging pipeline. It's really a very simple idea. You put a message on the one end, and it spits it on the other end. So why do you need a software for it? Because it's highly distributed, and it's highly reliable. So you know that if you put it on one end, think about a distributed system. How do you know which node got which message, and that they're delivered sequentially, and what happens if a message is lost? So Kafka does all of this well. You put in a message, it is queued, it is reliable, you can replay messages as well if something was missed. So the idea was that we write the data once, and we know that our system is eventually consistent. It's a distributed system. Consistency is something that we know is always going to be lower in our priorities, and that's okay. We're not a real-time shop. People can wait a little bit for their context to be searchable. So we write it once to Kafka, and then it puts it for you in Cassandra and Elasticsearch, and then we do all of our reads from Elasticsearch. Okay, that sounds cool, but Kafka is just the middle piece. It's just the messaging system. You still need something to be able to write from Node or whatever application into Kafka, and you still need the consumers, the pieces on the other end, to put the messages for you to, do some magic and put them in the right format. So on top of that, I added a platform called the Confluent Platform. And what it gives you is exactly that. It also gives you Zookeeper. It gives you a schema registry. Because Cassandra, even though it's a NoSQL, it is strongly typed. You define your tables beforehand. You define your columns, and they're strongly typed. So we can't allow a message to just have no schema. It gives you a node driver, the Confluent Platform. It gives us a node driver so we can put the messages in Kafka. And it even had a Cassandra consumer, but it did not have an Elasticsearch consumer. So we added another open source project called Data Mountaineers that does consumers. It had an Elasticsearch consumer, yay, but the consumer only did inserts. It didn't do updates, less yay. Okay, we'll do some work. We'll contribute to this open source project, and now it can do updates. Okay, so up until now, this is me on my laptop. I have it all set up, kinda, on my Ubuntu VM. It's kinda working, and we want to move it from prototype into make it a real app. I want to be a real one. Anyway. So we talked to the other GoDaddy teams, the data teams, and so on, and they say, yes, this setup, it's great, it's correct, it will work well for you. The only thing that you're missing here is FluentD before Kafka, and it doesn't really matter what FluentD is. It's another messaging system that's a little different and gives you monitoring in addition to all of that. But what's really important, or what was important at the time, was that I was trying to also add FluentD in front of Kafka. And it just wasn't working. But what was worse is that at this point, 2 other developers also joined the project. And they're trying to set all of this up, one of them on their Mac OS, the host, and the other one was trying to do it with Docker. And I still had been able to get FluentD running on my Ubuntu VM. And nobody's doing any development, like 3 developers. And everybody's just stuck on trying to configure this thing. And it's just not working. So at this point, I'm like, okay, time out. Time out. Like, do we actually need all of this incredibly convoluted system? Didn't we already say that Cassandra is our source of truth? We're not reading from it. We already added something to make sure that our Elasticsearch stays, that we keep it on track. Why do we need all of this? And the answer is, the answer we came to was that we really didn't. We don't need all of this extremely complicated setup in order to make sure that our data is in sync. What we decided to do is do synchronous calls to Cassandra and asynchronous inserts, updates into Elasticsearch through Sidekick. So it means that when a request comes into the server, when it comes back, we know that the data in Cassandra is true. That is its purpose, to be the source of truth. So when it returns, we know Cassandra is true, and then eventually it will find its way into Elasticsearch, and all of our searches are done with Elasticsearch. Now, as you might have noticed, Ruby showed up again, because at this point we decided, up until now it was a prototype. At this point we decided we're not going to do it in Node. We're going to go back to Ruby. While Node is considered more performant, and I will not argue that it is also, I'm just going to say, it's also really hard to develop against. Like, I've by now written the same code twice, right? Once in Node and once in Ruby. And it's just harder. You need to work harder. I at least need to work harder in Node. And we are, the Gem team is first and foremost a Ruby team. I mean, it is the language we develop in. We have an app that can handle a heavy load. And remember that this comes to support existing app. We know what is the expected load, and we know how Ruby can handle it. So at this point, the reasons to use Node, and also, again, our system does not need to be real time. It is okay for people to wait a little bit, especially for inserts, as long as they can get their data quickly enough, which is the Elasticsearch part. As long as it's in sync, we want the responses in quickly. So this is the setup that we ended up with. So a little bit about Elasticsearch. It's less interesting from the implementation perspective or how we integrate it. We're using the Elasticsearch Rails gem. If you're only going to use Elasticsearch, or if you're interested in introducing Elasticsearch into your app, I would recommend looking into SearchKick. It integrates with your active record, but it doesn't work for us with Cassandra. But what I really want to talk about next is about the Cassandra integration. So for Cassandra, we're using a gem called SQL. I'm going to call it SQL. It's how I call it all the time. And we're not using SQL, so it's OK. It's a domain locale. So as you can see, SQL has a very active record-like interface. I mean, we can set our ID, that's our partition ID, our columns with their type. We even have some basic has many relationships, validations, and lifecycle and hooks. But the thing is that under the hood, Cassandra, it is not a SQL, as I've mentioned. It is not a relational database. The idea in Cassandra, because you're starting to spread your data across different nodes, you can't just let one model to do everything for you, to answer all of your questions. So what you need to do when you start working with a NoSQL in general and Cassandra in specific, you need to start denormalizing. So you have different tables answering the different questions that you have, which is fine. You know, we've seen some SQL courses, some Cassandra courses, and read some articles, and consulted the data team, and we've designed our data in a way that kind of makes sense. But the problem that we've had is that we still designed our code in a very Ruby-like, active record-like way, because it lends itself so easily, but then it doesn't actually work under the hood. So a few weeks ago, I was pairing with one of the other developers, and he was trying to, or he did write a method that needs to answer a relatively simple question about the state of the object. It was a basic find or create, but it needed to answer it from a few different sources, and the answer was slightly different. And so he ended up with this incredibly long, incredibly convoluted, unreadable, unmaintainable method that we both agreed is not a good idea. And what we realized at that point is that we need to not only denormalize our data, we also need to denormalize our code. And instead of having this one long brain-hurting function, we broke it up into 3 different functions, where each function answered a slightly different question about the state from a slightly different place in the code. So if you do, there's a lot of trash talking Cassandra in our team, I'll have to admit. It's very hard to do the mind shift, and this makes it gives you an easy entryway, and if your data is small, it might seem like an easy transition. But at the end of the day, it's different than the traditional Ruby way, even to write code, not just to design your data. But it's definitely interesting. And the last thing I want to talk about is production. Right? So when I wrote the proposal for this talk, I was sure we're going to be in production by now, right? But as any production launches go, of course, we're not yet in production. We will be by the end of this month, I am sure. So I can't tell you much about how it actually performs, what are the things that worked or didn't work, what are the bottlenecks, and so on. What I can tell you is that we acknowledge that this is an experiment at the end of the day. We don't know for sure that it's going to work for us. We know that there is a situation where it might crash and burn. It could be that Cassandra is not the right solution. It could be that putting it into Elasticsearch is not working out well. This is an experiment for us. So I don't know, maybe next year I can come again and give you real data on how it actually works in production. So this is my GitHub handle and my Twitter handle. I will warn you that my Twitter, I've never tweeted in my life, but you're welcome to follow me there and hook up there. And that's it. Thank you.